On Earth, distance feels personal. A long drive can feel like an expedition. A flight can feel like crossing a world. But the moment you step outside the atmosphere, Earth shrinks into something that can't hold your attention for long. Because space doesn't scale with human intuition. It scales with numbers that feel like they belong to a different species. And the same thing happens with stars. Our sun looks enormous because it dominates our sky and powers every living thing we know. But in the universe, enormous is a sliding word. Out there are stellar bodies so large that the sun stops feeling like the standard. It starts feeling like the reference point you use to explain how ridiculous the giants are. In the southern constellation Scuti, astronomers have identified one of the strongest candidates for the largest star by radius we know today. But before we get to that name, we need to answer a more uncomfortable question. How big can a star actually get, and what stops it from getting bigger? Our sun has a radius of about 434,960 miles. That single number is already hard to hold in your head. So here's the classic scale trick. If the sun were a football, a soccer ball for Americans, Earth would be 109 times smaller. On that scale, Earth is a peppercorn about 2 millimeters wide. And the sun isn't just big, it's heavy. Even if you added up the mass of every planet in the solar system, the sun would still be about 743 times more massive than all of them combined. So yes, the sun is huge compared to the worlds that orbit it. But compared to other stars, it's middle of the pack. Alpha Centauri's main stars are in the same general class of size, and Sirius A is roughly twice as large. To find the true giants, we need to stop thinking in snapshots and start thinking in life cycles. There's a map astronomers use to understand stellar lives at a glance. It was developed independently in the early 1910s by Einar Hertzsprung and Henry Norris Russell. Today, we call it the Hertzsprung-Russell diagram. It plots stars by temperature and luminosity, and it reveals a spine running down the center, the main sequence. Most stars spend the majority of their lives there, in a stable phase called hydrostatic equilibrium. Fusion in the core pushes outward, while gravity pushes inward. Neither side wins, for a while. Our sun sits near the middle of that band as a G-type main sequence star. The letter is part of a temperature classification system, OBAFGKM, where O is hottest and M is coldest. The naming is awkward, but it works. G-type stars like the sun have surface temperatures around 5,778 Kelvin. In the core, hydrogen fuses into helium, converting about 600 million tons of hydrogen every second into energy. That energy has powered life on Earth for billions of years. Now move up the main sequence, and the pattern becomes violent. Hotter stars are brighter, and usually more massive, and mass is the lever that changes everything. Take Bellatrix, the 26th brightest star in the night sky, and the left shoulder of Orion. It's a B-type star with a surface temperature around 22,000 Kelvin, almost 4 times hotter than the sun, and it's about 8.6 times more massive. That extra mass crushes the core with greater pressure. Higher pressure increases the fusion rate, which increases luminosity, which increases internal push. The star swells as if gravity can barely hold it together. Bellatrix ends up with a volume about 200 times greater than the sun's, but the trade is brutal. Massive main sequence stars burn hot and fast. The sun will likely have a total lifespan of about 10 billion years. Bellatrix has been burning for roughly 25 million years, and may have only about 7 million years left. That's why the truly massive stars are rare. They don't last. So does the largest star simply mean the most massive star? Not necessarily. There's a practical ceiling to how massive a star can be at birth. It's thought that stars struggle to form much beyond about 150 times the sun's mass without becoming so unstable that they tear themselves apart. But the universe has a way of cheating. When massive stars collide and merge, the result can exceed what a single star could safely form as in one piece. One famous example is the staggeringly named R136A1. It sits at the extreme top left of the Hertzsprung-Russell diagram, hot, luminous, and violent. Its mass has been estimated at about 265 times the mass of the sun, with a radius about 40 times larger. R136A1 belongs to a rare class known as Wolf-Rayet stars. We've found just 220 in the Milky Way, although scientists suspect there could be as many as 2,000. Wolf-Rayet stars are unstable and short-lived. They throw off plasma in powerful winds, ejecting as much as 10 solar masses every million years at speeds up to about 1,864 miles per second. That is not a gentle breeze. That is a star actively dismantling itself. R136A1 is also absurdly luminous. It can release as much light in just 4 seconds as the sun produces in a year. And yet, to human eyes, it's only about 164,000 times brighter because much of its output is ultraviolet. We're lucky to catch it at all. It likely exists for only about 3 million years, a blink on cosmic timescales. But even that doesn't make it the largest star by radius, because size and mass don't scale the way most people assume. The truly enormous radii show up late in a star's life. When a star runs out of hydrogen in its core, the balance breaks. The core begins to collapse, pressure rises, temperatures rise, and new fusion processes ignite. That heat changes the structure of the star. Fusion can begin in shells outside the core, and the outer layers inflate dramatically. The star becomes a red giant. Our sun's radius today is about 435,000 miles, but as a red giant, it's expected to expand to a diameter of about 186,411,300 miles, large enough to consume Mercury, Venus, and possibly even Earth. This red giant phase can happen for stars with about 0.8 to 8 times the mass of the Sun. A living example is Mira A in the constellation Cetus. It's only about 1 to 1.2 times as massive as the Sun, yet its radius is at least 332 times larger. And Mira isn't steady. It pulses through cycles ranging from 80 to 1,000 days. When those cycles align, the star physically puffs up, and its maximum radius can reach around 402 times that of the Sun. So red giants can be enormous, but they still aren't the largest class by radius. Once you cross into higher masses, another category dominates: the red supergiant. Betelgeuse is a famous example. It has a diameter of around 745,645,200 miles. That makes it more than 700 times the size of the Sun by diameter. If you dropped it into the center of the solar system, it would engulf the inner rocky planets, and even Jupiter wouldn't be safe. These stars are violent at the end of their lives. They pulse, they shed material, and their outer boundary becomes fuzzy. It's not always obvious where the star ends and space begins. And yet, even Betelgeuse isn't the biggest candidate. In Scutum, there is a star that often takes the crown in popular discussions: WOH Scuti. WOH Scuti is so large that about 5 billion suns could fit within it. And it's not even particularly hot. It's about 40% cooler than the Sun, glowing a deep, subdued red. Because it's distant and relatively cool, WOH Scuti isn't visible to the naked eye. You need strong binoculars or a small telescope. Distance estimates place it somewhere between 5 to 10,000 light-years away, which creates uncertainty in its true size and leaves room for other contenders. WOH Scuti also doesn't have long left. It's already about 10 to 20 million years old, and it may have only a few million years remaining. In that time, it could even shrink, transitioning into a yellow hypergiant as it sheds its outer layers and heats up again to sustain its final fusion stages. Hypergiants can lose mass in spectacular bursts. In one explosive burp, they can blow off an amount of mass comparable to Jupiter, and they can do it more than once. Those ejections are packed with heavy elements like oxygen, carbon, and nitrogen. Over time, they can form vast clouds around the star, sometimes reaching about 10,000 astronomical units in length, roughly 300 times the distance from the Sun to Neptune. That material matters. It mixes into dust clouds and stellar nurseries, feeding the next generation of stars and planets. This is how the universe recycles itself. Now push beyond the Milky Way. We've only ever properly imaged one star outside our galaxy in true detail. It's called WOH G64. a red supergiant in the Large Magellanic Cloud. WOH G64 is about 160,000 light-years away, and recent studies suggest that in just the last 10 years it has become dimmer, throwing off material and becoming shrouded in dust as it changes state. But at these distances, measurement is hard. WOH G64 might be bigger than UY Scuti, or it might not. When you're dealing with objects this far away, uncertainty becomes part of the story. There's also a physical boundary called the Hayashi limit. It effectively marks the maximum radius a star can reach for a given mass. If a star pushes beyond it, convection takes over, gravity gains the upper hand, and the star contracts. So we may eventually find a star slightly bigger than UY Scuti, but it likely won't be bigger by much, unless there's a category of giant we simply haven't observed in our galaxy. And there's a humbling truth hidden in all of this. Humans struggle to intuitively grasp anything larger than a few thousand miles. The largest stars stretch far beyond our mental scale. They are cosmic monsters. But even the monsters are small in the bigger structure. Galaxies are tens of thousands of light-years across. They sit millions of light-years apart. And the filaments of the cosmic web stretch billions of light-years through space. The universe is so vast that our best descriptions still feel like approximations. But the fact that we can measure these giants at all, and compare them, is one of humanity's quiet victories. And maybe the final lesson is this: bigger isn't always better. Living on a tiny planet around an average star has worked out pretty well so far. They are temporary extremes, swelling, shedding, and racing toward a final collapse that seeds the next generation of worlds. They are not stable monuments, which makes the giants feel even more dramatic. That is the universe's strange trade. The biggest stars are often the ones closest to the end. The widest radii tend to come late, when a star's internal structure shifts and the outer layers inflate. Massive main sequence stars can be the heaviest and most luminous, but they're not always the widest. And yet, even with all that uncertainty, the overall pattern is clear. We can map some surfaces, but others are still just points of light with error bars. We find nearby ones more precisely than distant ones. We find bright giants more easily than dim ones. And the sample is biased. It's the largest within our current sample, measured with our current tools. That's why the title largest is always provisional. A star can look larger in infrared than in visible light, simply because you're tracing different layers. So radius measurements can depend on wavelength, method, and model assumptions. Others have atmospheres that blur into surrounding dust. Some giants are wrapped in thick winds and expanding shells. Their outer layers can be extended, turbulent, and partially transparent. Stars don't have a clean edge like a rock does. One last subtle point makes the hunt for the biggest star harder than it sounds. Speaking of planetary mysteries, there's something strange about Mercury and Venus. They're the only planets without moons. Jupiter has 92. Saturn has over 200. But these two? 0. Watch our video on why Mercury and Venus don't have moons to discover what the sun's gravity does to everything nearby.